Good day, I'm Norman Wamberger. Today we're going to have a little bit of fun working out what the curvature of a parabola might be. We're actually going to get a very explicit formula for it, which is basically a classical well-known formula. But the novelty is that we're going to do it without any calculus, without any differential geometry, without any angles or real numbers. So yet another small piece of evidence that it is possible to do mathematics completely correctly, algebraically, logically, without any infinite processes. Slowly we're going to accumulate more and more examples of such things till we end up really having a viable alternative to the current status quo. Okay, so the notion of curvature is very classical. It goes back to the 17th century, the beginnings of calculus and, in fact, Cartesian geometry. And I think it was probably Huygens, the Dutch mathematician, astronomer, who first came up with the idea. So here's a curve, gamma, and the idea is that at any point on the curve, we can approximate the curve, well, first of all, with a straight line, which is the tangent. But sort of one step up from that, we can also hope to approximate the curve near that point with a circle. There is some circle which goes through that point and is also tangent to the curve with the same tangent line, and which really best approximates the circle. Now that might be a circle with a small radius or a bigger radius, depending on how sort of curved the curve is at the particular point that we're interested in. So the official definition is that the curvature, little k, is 1 over r, where r is the radius of this circle which best approximates the curve at some point A on it. So for here, if that's the point A1, then the curvature at A1 of the curve gamma would be 1 over R1, 1 over this radius here. And the curvature of the curve at the point A2, well, that would be, K2 would be 1 over this radius R2. So that's the classical notion of curvature, which of course is not so convenient for us because there's lengths involved. These radii are lengths, and so they have square roots, and so that's a story that we would rather avoid if we could. So how did the 17th century mathematicians calculate curvature? For example, here's a curve, and here's a point on the curve, say A. How would we calculate what the curvature of the curve at that particular point is? Well, there's a couple of different ways of approaching this, and here are perhaps the two simplest ways of explaining it. So one formula is that the curvature is d theta ds, the rate of change of the angle of inclination of the tangent with respect to arc length. Okay, there's obviously a bit of calculus involved here. We're not going to fuss around about it too much, but basically the arc length is, according to the standard dogma, the length of the curve from some base point. So if we fix some base point here and we somehow measure the length of the curve, whatever that means, then that's a quantity that varies as we move along the curve. And we're also interested in the tangent at some point. So as we move along the curve, the tangent is going to move as well. And if we are always recording the angle that this tangent makes with the, say, x direction, call that theta, then the rate of change of that angle with respect to this arc length is another way of getting at the curvature. So if the angle is changing a lot for a small sort of increment of length, then the curvature is high, and otherwise it's low. Okay, another way of thinking about what it is sort of geometrically. We can sort of construct the curvature geometrically by taking some nearby points, B and C, to the point that we're interested in, still on the curve, and then we can, say, join the lines from A to C and A to B and take perpendicular bisectors of those two segments. Where they meet will be the point which is the center of the circle which passes through those 3 points. Okay, that's the basic construction of the circle that passes through 3 points. Now, that's not exactly the approximating circle that we want, because B and C are not exactly at A. But if we then start moving B and C closer to A, then it turns out that this circle starts approaching some limiting circle, and then the quantity, the curvature that we're interested in, is sort of the limit of this radius here, the inverse of this radius, as B and C approach A. It's kind of a geometrical way of visualizing what is going on here. This is very classical, and the 17th century mathematicians liked this idea a lot and proved theorems and made calculations to compute curvatures and these corresponding sort of centers of curvature for various classical curves. So that discussion is for us very problematic because it rests on a whole lot of things that, first of all, we're not quite sure about, and also some other things that we haven't developed. We certainly haven't talked about calculus yet, and so there's no need for us to invoke calculus ideas. But in fact, the notion even of the curve itself is problematic. This is another kind of general concept that, although it's easy enough to write down lots of examples of things that ought to be curves, to actually say precisely what a curve is surprisingly complicated. And the 17th and 18th century mathematicians realized this. They were not unaware of this. So we can be more precise by being more restrictive. In other words, by setting our sights a little bit lower, trying to bite off a little bit less, we can hope to do the job a little bit more carefully and accurately. So what we're going to do is aspire to something less. We're going to restrict ourselves to much simpler kinds of curves that we can actually bring into existence completely solidly. So we'll go back to our polynumbers. You remember, polynumber is a list of numbers like this kind of notation. There's a polynumber p. And it's a quadratic polynumber because there's only 3 entries to it. So it corresponds to a degree 2 expression, 2 minus alpha plus 3 alpha squared. And we can think of this as being the quadratic polynumber, just another way of writing the same thing. So associated to this, we can associate a curve by graphing this. So we can take this polynumber and we can create this expression from it, y equals 3x squared minus x plus 2, in the same spirit that we defined a circle as x squared plus y squared equals 1, or x squared plus y squared equals x. Okay? So this expression, we can say, is a quadratic curve. And it's an expression that derives from this quadratic polynumber. And since we understand quadratic polynumbers completely, we have complete control over what the range of possibilities are for such things. And here is the graph of such a thing. It's, as we all know, a parabola opening upwards because that coefficient is positive, and it goes through a few points that we can plot. Okay, so we are going to be a little bit more restrictive. We're going to be interested in trying to figure out what the curvature of such a quadratic curve is. Of course, it's going to depend on which point we choose. Obviously, the curve is a little bit more curved here than somewhere up here. Here it's getting a little bit more straight. Here it's quite curved. Okay, so to bring things into focus, we're going to choose our simplest parabola, y equals x squared, which has the familiar diagram that we've all seen many times. There it is there. And we're going to choose an arbitrary point on it. Call that point A, and it has coordinates t squared. So we're just basically choosing an x-coordinate, and then the y-coordinate will be the square of that x-coordinate. So there's t squared. And we're interested in calculating the curvature of this parabola at that point. And what we're going to do is we're going to use this basic fact that we've been talking about in our last video, that if we have a circle of circumquadrants r, so capital R is not the radius but the square of the radius, so actually the quadrants from the center to any point on it. And if we have 3 points on that circle forming a little triangle, then that triangle has quadrants as Q1, Q2, and Q3, and has quadria A. A is also 16 times the square of the area. Then we saw that in this case, the curvature of that circle, which is by definition 1 over this circumquadrance R, turns out to be this lovely expression, the quadria divided by Q1, Q2, Q3. So it's essentially the quadria sort of renormalized by the product of the three quadrances. So this works for a triangle on a circle. So we're going to apply this to a triangle on the parabola. Okay, so here's our parabola again, y equals x squared. And now we're going to choose 3 points. Say A1, which is T1, T1 squared, A2, which is T2, T2 squared, and A3, which is T3, T3 squared. And at first we're not going to assume that these are anywhere special. They're just any points on the parabola. And now we're going to basically make a small calculation. And really the essence of the entire calculation is really on this page. It's a little bit like magic. Okay. So we're interested in two quantities. We're interested in this quadria A formed by this triangle here. And we're interested in the product of these three quadrances, Q1, Q2, and Q3. All right, so let's start with A, the quadria of this triangle, which is also the Archimedes function applied to the three numbers Q1, Q2, and Q3. That Q1 plus Q2 plus Q3 squared minus 2 Q1 squared plus Q2 squared plus Q3 squared expression. But I remind you that we had an alternate way of thinking about the quadria in terms of actually the coordinates of the 3 points. If we know the coordinates x and y of the 3 points, then we can write down another expression for this quadria. It's 4 times this quantity squared. And this quantity is obtained by taking the x1 times y2 minus x2 times y1 expression for this pair, and then a corresponding expression for this pair, and a corresponding expression for this pair, and adding them all up. So we get t1 times t2 squared minus t2 times t1 squared from these 2 points. And then similarly, moving to these ones, we get t2 times t3 squared minus t3 times t2 squared. And now moving to these 2 points, we get t3 times t1 squared minus t1 times t3 squared. And you should think about this as that little grouping, that little grouping, and that little grouping. And to go from one of these groupings to the next grouping, we just bump each one of the indices up cyclically by 1. So going from 1 to 2, from 2 to 3, and from 3 to 1. Okay, very pleasantly, what's inside the brackets here ends up being this quantity here, or perhaps with a minus sign. But when we square it, the minus sign doesn't become involved. So we just end up getting 4 t1 minus t2 squared, t2 minus t3 squared, t3 minus t1 squared. This expression, the quadria, is exactly this pleasant product of the squares of the differences between the coordinates. That's like magic, but it shouldn't really be a big surprise to us, because if we think for a second and say, well, this depends on t1, t2, and t3. There are these 3 numbers floating around. Now if t1 happened to equal t2, then these 2 points would coincide, and that triangle that we have would degenerate, and so its quadria would be 0. And that's telling us that t1 minus t2 ought to be a factor of this quadria. Similarly, t2 minus t3 ought to be a factor, and t3 minus t1 ought to be a factor. And then since the whole thing is independent of ordering, because the quadria is independent of the ordering, it's not a surprise that there are squares here. Great. Okay, so that's half the battle. That's the numerator of the expression we're interested in. And what about the denominator? Well, that's the product of these q's. So let's calculate q1. The quadrants between, say, A2 and A3. Well, that's pretty simple. It's just the difference in the x coordinates squared plus the difference in the y coordinates squared. If we stare at this for a second, we see that this one here, which is a difference of squares, will also have this t3 minus t2 factor inside it. So we can factor out t3 minus t2 squared. And there'll be a 1 from this term, and there'll be a t3 plus t2 squared from this term. because T3 minus T2 times T3 plus T2 is T3 squared minus T2 squared. So since there's a square there, there's going to be a square here and a square there, and that's a nice expression for Q1. Okay, and similarly, there's a completely analogous expression for Q2 involving the T3s and T1s, and for Q3 involving the T1s and T2s. So we have all our ingredients. We can just write down our curvature for this triangle here. Okay, we haven't actually got the curvature at a point yet. We've got the quadratic curvature of this triangle, essentially. All right, so going one step at a time. First, the circumquadrants of the triangle that we're interested in. The quadrants of that circle that passes through those 3 points will be the product of the cues divided by the quadria. Okay, and that turns out to be this term times this term times this term divided by 4. Because we've just canceled this factor T1 minus T2 squared, T2 minus T3 squared, and T3 minus T1 squared. That will be common in the numerator and denominator here. After all, the quadria was just 4 times this thing, and the Q1 was this thing times this. The Q2 will be this times this, and the Q3 will be this times this. So this factor will appear both in the numerator and the denominator, and happily we can cancel them both from the numerator and denominator. Okay, so then the curvature, which is actually what we're really interested in, is going to be the reciprocal of the circumquadrants. It's 1 over r. We just flip this thing over, and we get 4 over 1 plus T3 plus T2 squared times 1 plus T1 plus T3 all squared times 1 plus T2 plus T1 all squared. So what that's a formula for the curvature of the circle which passes through 3 arbitrary points on our parabola. There's A1, A2, A3, given by these x values T1, T2, and T3. And here's an expression for the curvature of this circle that passes through those 3 points. So now if we look at that expression for the curvature of this general triangle on the parabola that we just derived, involving T1, T2, and T3, we see that there's nothing to prevent us from actually setting them all equal to each other. Setting T1 equals T2 equals T3 equals, say, some value T. Then each of the terms in the denominator are the same. They're all 1 plus 4t squared. Because it would be something like T1 plus T2 all squared. If T1 and T2 are equal to T, then that's like 1 plus 2t squared, or 1 plus 4t squared. And there will be 3 such factors. They'll all be the same. So we get 1 plus 4t squared cubed on the bottom, and the 4 that was there on the top. Okay, so we can think about what this is some kind of limiting value that we get when we let T1, T2, and T3 all move, these 3 points on the x-axis, all move towards the value of t that we're interested in for our original single point A. But really, we're not really taking a limit as such. Okay, there's no real process of getting closer and closer and closer. We're not doing that. We're just taking this expression and replacing T1, T2, and T3 with T, just like that. It's a purely algebraic replacement. Now, if we think back to the previous step, before we canceled, there were factors T1 minus T2, T2 minus T3, T3 minus T1 in the numerator and denominator. If at that point we had plugged in T1 equals T2 equals T3, then we would have gotten 0 over 0. So at that stage, we were not allowed to sort of bring all the t's together. But happily, once we've actually let the algebra run its course, and the algebra has given us an expression, nice rational expression for this curvature, then we can do this. And so it does make sense to define this to be the quadratic curvature of the parabola at the point A equals t squared. In other words, the definition of the curvature of the parabola at this point A can be this. So this is the procedure that we adopt. We calculate an expression for this quadratic curvature of a triangle, a general triangle on the parabola, and then if we can, we replace each of the points with a single point, and if we get something that makes sense, well, that's going to be our quadratic curvature. This is not a new formula. It's perhaps a somewhat novel derivation of it, but the curvature of the parabola has been well studied for centuries. So classically, the classical curvature, which is little k, is the square root of our k. So if we take a square root, then we have 2 here, and we have to take the square root over here. So there's going to be a 3 over 2. So for example, if t is equal to 1, up here we would get a 1 plus 4, that's 5 cubed. So the quadratic curvature is 4 over 125. Classically, the classical curvature, little k, would be 2 over the square root of 125. And of course, by now you're quite expecting me to say, and that's of course no problem because we just take a few million trillion years calculating this square root of 125, as we always do, right? To infinity, and then we have the square root of 125. So this little equation involves an infinite amount of work. This equation involves about 10 seconds work. We just plug in t equals 1 and evaluate it. We get 4 over 125. End of story. That's the quadratic curvature. It's not just a small difference between these two things. It may appear to be a small difference. It's a huge computational difference. And a rather significant conceptual difference too. Okay. Don't minimize the big step up going from here to here. This is the right way of thinking, for sure. Okay, so good. This has been a lot of fun. So you'll probably want to calculate some curvatures for other curves. And I suggest that you try it for the other simple sort of polynomial curves like y equals x cubed or y equals x to the 4th. Or if you're feeling ambitious, you can try y equals x to the n, the general case. And I hope you appreciate sort of the power and the elegance of applying this formula, really coming essentially from this one-dimensional projective geometry. It's really the projective triple quad formula in action that's really behind our curvature formula. In our next video, we're going to go back to that projective one-dimensional situation which gave us this very rich formula and go a little bit further. We're going to look at not just 3 projective 1 points, but 4 projective 1 points and ask the same kind of question that we did originally on the line. Once we established a triple quad formula for 3 points, eventually we said, well, what happens with 4 points? And that turned out to be very interesting, connecting to Brahmagupta's formulas, Robin's formulas. So we're going to do the same kind of thing. It's a very natural thing to do. Probably you've been waiting for me to do this. Okay, so we're going to go back. We're going to look at the projective quadruple quad formula. What is it? You might like to see if you can figure out what it is before the next lecture. So I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.